In this video, we're going to explore Hugging Chat and demonstrate how to use various prompts to get various answers. Hugging Chat is a generative AI model similar to ChatGPT. However, there are some differences with Hugging Chat. One of the major differences between Hugging Chat and other prominent generative AI models is that Hugging Chat is open source. This means that unlike its proprietary competitors, we can go in and examine the source code of Hugging Chat and see exactly how it works. This also means that as an open source project, users are able to access and modify the source code of Hugging Chat in order to continually improve and add new features as well as fix existing bugs. Now, Hugging Chat is also not nearly as mature as something like ChatGPT. So the results and the outputs that you get from Hugging Chat may not be as reliable as some of the more well-known generative AI chatbots. Another differentiator that Hugging Chat has is that we don't need to be logged in or to create an account before we can use the chatbot. We can use Hugging Chat anonymously without being signed in. To get started with Hugging Chat, open up a web browser and navigate to the URL seen at the top of my screen. https://huggingface.co/chat. When you navigate to this website, you'll be met with the Hugging Chat landing page. Before we get started with asking prompts to Hugging Chat, we can see that it gives us some information about the model itself. In the upper right, under the current model header, we can see that Hugging Chat is running meta-llama/llama-2-70b-chat-hf as its current model. And if we want to get more information about that model, we can click the website button in the bottom right of that current model window, and that will lead us to the website for the Llama model. Here we can get more information about the Llama model that Hugging Chat is using. But for now, let's just stick to the Hugging Chat webpage. When we're ready to start asking some prompts, we can go to the bottom of the page and click in the text bar that says Ask Anything. We have a few examples given to us on this page as well. In the middle of the page, there are 3 examples. 1. Write an email from bullet list. 2. Code a snake game. Or 3. Assist in a task. So let's try these examples. I can click on the first one, Write an email from bullet list, and it starts to generate some answers. And now the generation of our prompt is complete. So we have in front of us an output box that is generated based on the input that we used. So the input that was used by Hugging Chat for our example was, as a restaurant owner, write a professional email to the supplier to get these products every week. 10 bottles of wine, 24 eggs, and 12 loaves of bread. And then based on this prompt, Hugging Chat has created and crafted that email for us with fields that we need to replace ourselves denoted by square brackets. So for example, we have Dear Supplier's Name at the top of the prompt. It's expected that we would replace this with the name of the supplier that we are emailing. These square bracket replacements are present throughout the entire generation, so we need to make sure that whatever we are generating and using, we parse through ourselves to replace the relevant information. It's also interesting to note that as the generation happens, there is a delay with the generation. It doesn't all come as one big block. And that's because every word is generated individually. For every word, the model goes through and calculates what the most likely word is going to be in that location based on the word or words that have come before it. And then it repeats its process for the next word and the next word until the generative process is done. And this is why we see the delay as each subsequent word is calculated. Now I'll click back on my browser to go to the next example, and let's click on Code a Snake Game. And now in this case, our prompt is code a basic snake game in Python and give explanations for each step. The prompt can be seen at the top of the window, and now we are getting programmatic step-by-step output of how we can code that snake game. And it gives us the steps in order, going from importing the necessary libraries to initializing Pygame, all the way through the process of creating a snake game in Python. And now that the generation has finished, we have a complete step-by-step guide as to how we're going to go about creating this snake game in Python. This can be very useful if you're trying to learn a new programming language or a new programming idea. Once again, I'm going to hit back on my browser and go back to the main screen and click on the third example, which is Assist in a Task. And the output that we're using now is, how do I make a delicious lemon cheesecake? Which can be seen at the top of my screen once again. And at this point, the generative AI is creating a recipe for a lemon cheesecake. And now that our generation is finished, we have a recipe for creating that cheesecake. However, this brings up a good point to consider when working with generative AI. There is no guarantee given by a generative AI that the output that it is presenting to you is correct in any way. This is especially important in this particular case where we're dealing with a physical process. The generative AI might produce a recipe and procedure that is dangerous. There is no guarantee that the ingredients it tells you to use will mix properly or will be used in a safe way, and that the procedures that you're supposed to follow are safe for use. So it's very important that we don't take everything that the generative AI says or outputs to us as fact. We need to parse through ourselves and make sure that what it is telling us to do makes sense and is safe to do. So for example, we see step 1 is preheat your oven to 350 degrees Fahrenheit. This seems pretty reasonable, but what if it had said preheat your oven to 800 degrees Fahrenheit? Well, this is significantly hotter than most ovens are supposed to go or generally go. And as a result, if you followed the instructions without parsing it yourself, you would put your oven and your house into a dangerous situation. So it's important to understand this fundamental concept of generative AI, that it does not produce you with a correct answer. The chatbot will always give you an answer, but it will not always give you the right answer. So these are some of the ways that we can use generative AI to get ourselves some output or some answers to various questions or requests. For the most part, all generative AI works fairly similarly. So whether you're using Hugging Chat or ChatGPT or any other generative AI chatbot, you will interact with it in very much the same way. In this video, we're going to show how we can use AI to enhance an existing security tool or process. For this demonstration, we'll be using a hypothetical scenario where our network analysts want us to train an AI model to help them identify malicious behavior in packet analysis and log analysis procedures. And specifically, they want our AI model to identify UDP-based DDoS attacks. Now, to train our AI model, we're going to be using a dataset available from the University of New Brunswick. To access this dataset, navigate to the URL seen at the top of my screen in the URL bar, https://www.umb.ca/cic/datasets. And then on this page, scroll down under Available Datasets and expand the list underneath IDS Datasets. And then we'll click on DDoS Evaluation Dataset, which takes us to this page explaining everything we need to know about the dataset. And if we scroll down to the bottom, there is a link to download the dataset. So this is where you can get the dataset that we're using in this demonstration. However, as with anything related to malicious behavior, exercise extreme caution when downloading files from the internet, and make sure that you do your due diligence on anything that you're trying to source, even if it is from a reputable provider, before bringing that into your own environment. In this demo, we will be working in a Windows system, so everything we're doing is going to be in a Windows PowerShell window. Once you have your Windows PowerShell window open, we'll need to start up Python. To check whether or not Python is installed on your system, type in Python and hit enter. If an interactive terminal starts up, giving you the Python version and the triple chevrons indicating the interactive environment, then you have Python properly installed. Next, we'll need to install some packages or libraries that we need to work with in order to train our AI model. The first is scikit-learn, which is the machine learning library that we'll be using. To install that, we use the command pip3 install -U scikit-learn and hit enter. Next, we need to install the pandas library, which is how we're going to work with our dataset. Once again, we'll use pip3 install -U pandas. Now let's start building our model. So to do that, we'll start up our Python interactive terminal once again with the command python. And now we're going to import our required libraries. So I'll import the following libraries. Import pandas as PD. I'll import numpy as NP, which is going to help us when working with our arrays. Then from sklearn, I'm going to import the pre-processing library to help us with normalizing and processing our data. Next, I'm going to import train test split from sklearn.modelSelection, which will help us with dividing up our dataset into training and testing sets. Next, I'm going to import logistic regression from sklearn.linearModel, which is the algorithm that we're going to be using to train our model. And we'll be using a classification style algorithm in order to decide whether a given piece of traffic is malicious or not. Next, I'm going to import the Jacquard score from sklearn.metrics, which will give us a way of evaluating the accuracy of our model. And now I've just cleared my screen to clean things up a little bit so that we can go back to the top of our terminal. And we're going to import one final library, which is classification report from the same sklearn.metrics library. And now we're ready to get started with our code. The first thing we'll need to do is read in our data into a variable. Our data is saved as a CSV format, so we're going to use the pandas library to do that. So I'm going to call my variable mal_df equals pd.read_csv. And now I'm going to be passing it a Windows file path, so I'm going to preface this string with the letter R, double quotes, and then the path to wherever your dataset is stored. And then close the double quotes and close the bracket, and hit enter. And this will read that CSV file into a data frame for us. Now that our data frame is loaded, we can take a look at what our data looks like. So I'm going to just type in mal_df into the console and hit enter. And now this is showing us our first few rows and our last few rows in the dataset. And then along the top, we have the column names. Now there are about 80 columns in this dataset. So once again, the data is truncated and only showing us the first few column names and the last few column names. If we want to see the shape of this data, we could call mal_df.shape. And it tells us how many rows and columns are in this dataset. So we have 3,782,206 rows in this dataset and 88 columns. Now we're going to need to pare down how many columns or features we actually use in our training model because we're not going to be using every single column. Oftentimes, not every feature is going to be relevant to what you're trying to train, so we're going to pare down only the features or columns that we consider to be relevant to our model. So let's take a look at what all of the columns are, and we can do that by calling mal_df.columns. And now we have a full list of all the columns or features in our dataset. So from this, we're going to pick a subset of the features that we want to use to train our model. An important point here is that annoyingly, some columns, such as flow ID, start without any white space, but some columns like source IP start with one character of white space before them. So it's important that when you're specifying the column, you know whether the column has white space before the text starts or not. So to pick our dataset features, we're going to pare down the columns. We do that by saying mal_df equals, and we're going to set it equal to mal_df, square bracket, square bracket, and now the list of features or columns that we want to include. In this case, we're going to include source port, destination port, protocol, total forward packets, total backward packets, flow bytes per second, flow packets per second, and label, and then close it with two square brackets. This last feature that we chose, label, is actually what our AI model is going to try to predict. This label is going to tell us whether something is malicious or not. So now that our dataset has been pared down, let's take a look at it again by calling mal_df. And now we can see that all of the columns are present, and we've removed a significant number of them. So all of the columns that we specified are now present in our dataset: source port, destination port, protocol, total forward packets, total backward packets, flow bytes per second, flow packets per second, and label. And all of these columns, except for label, are going to be used to predict the label. Now, if you remember back to our hypothetical scenario, we decided that we're going to specifically train for UDP-based DDoS attacks. So in our case, anything that's labeled as UDP, we're going to classify as malicious. So we're going to convert that into a numerical value to allow our AI model to work with it. So what we'll do is we'll specify anywhere that there's UDP present, we're going to change that to the number 1, indicating malicious. And if the label is anything other than UDP, we're going to label it as 0 or not malicious. We'll type in mal_df, and then we're going to pass a few values to this replace function. The first is to_replace, and we're going to set that equal to UDP. And then we're going to specify value, and we're going to set that equal to 1. Then we're going to specify inPlace equals true to make sure that it does the actual replacement on our variable. And we'll hit enter. Now, let's take a look at our dataset again by typing in mal_df. And if we look over in the far right on the label column, we can see that anywhere that there was UDP before is now the number 1. Our next step is to replace all the other values with 0. So to do that, we'll type in mal_df, specify the label column, and we'll set that equal to pd.to_numeric. And as arguments to this function, we'll pass in mal_df label column, and we'll set errors equal to coerce. Then we'll call .fillNA 0, and finally we'll call .astype int. And so what this is going to do is go through our label column, and anywhere that it finds a value that isn't a number, it's going to replace it with a 0 as an integer. So now let's look at our dataset once more by calling mal_df. And we can see in the label column on the far right, all of our values that were not UDP are now 0. So we're almost there in terms of our data, but now we see that in the second row, under flow bytes and flow packets, we have infinite values. So now we need to get rid of those infinite values so that we're only working with numeric values. To do that, we're first going to replace all of our infinite values with not a number values. And we'll do that by calling mal_df.replace once again. And we're going to pass it a list of both infinite and negative infinite values, which we specify as np.inf and negative np.inf. Then we'll specify np.nan, which is the value that we want our infinite values to become, which stands for not a number. And once again, we'll set inPlace equal to true. Let's look at our dataset again with mal_df. And our infinite values under flow bytes per second and flow packets per second are now not a number. At this point, we can drop all the not a numbers using the drop_na function on our data frame. So to do that, I call mal_df.dropNA, and I specify inPlace equals true again. And the values that we wanted to be removed have been removed. Our next step is to define x and y for our dataset. X will be our features that we use to predict, and y will be the label that we are trying to predict. So first, I'll list out our columns using mal_df.columns, and then I'm going to specify x equals np.asArray, mal_df, square bracket, and I'm going to paste in all of the columns except for label, and then close it with a square bracket, and a round bracket. Next, I'm going to specify y using the same method, y equals np.asArray, mal_df, square bracket, and then we'll pass the label column. Now we want to normalize these values, so we'll use the preprocessing library for that, saying x equals preprocessing dot standard scalar dot fit x dot transform x. And now if we look at our array, we can see that the values have been changed to be normalized. Now we need to split our data set into training sets and testing sets. So to do that, we'll type in x_train, x_test, y_train, y_test, and set that all equal to train test split. Then we'll pass in x, y, a test size of 0.2, and a random state of 4, and hit enter. Now we can look at the various shapes of our training sets and our testing sets using xtrain.shape and ytrain.shape, which shows the respective values in terms of rows and columns in our training dataset. In this case, 2,964,127 rows, and we could do the same thing for the test set as well if we wanted to. So now let's create our logistic regression model. We'll call it log_reg, and we'll set that equal to logistic regression. We'll set our C parameter to be 0.01, which is a regularization parameter, and then we'll set our solver equal to liblinear, which is a numerical optimizer parameter of which there are various values, and we'll fit it on our training sets, xtrain and ytrain. And hit enter. So now we have our model trained on our training sets. Now we can start to make some predictions with our model. So we'll call our predictions y_hat, and we'll set it equal to log_reg.predict, and we'll pass in the testing set, xtest. Now, if I want to see the output of y_hat, I can type in y_hat, and it gives us an array of values. In this case, anywhere that we see a 1, it means that the model has detected that that particular network packet or network transaction is classified as malicious. Now let's take a look at the Jacquard score of our model. So we call Jacquard_score, and we pass it ytest, yhat, and pause label equals 0. And we can see a Jacquard score of 0.44. Now that's not a very good score, but we also just picked the features randomly, and we didn't put a lot of thought into how we're training our model in particular. So there is a lot of room to improve the accuracy of our model. Some of the ways that we could improve the accuracy of our model is we could go back to our feature set and pick out more or better features. If you remember, we pared down the first feature set fairly arbitrarily. So if you did more research to see which features have the higher weighting and are more critical to the prediction model, you could improve the accuracy of the model by including or excluding different features. You could also tune the values of your algorithm or use a different algorithm. We used a logistic regression model for classification, but there are also other options that might fit the data better. So it's important to realize that there are many different variables at play when working with these AI models, and you need to iterate with the model to get the best possible accuracy that you can. And finally, let's look at the classification report. So I'll print classification_report, and I'm going to pass it ytest and yhat once again. And now here we have values like precision, recall, F1 score, and support. This gives us further accuracy about our model. So now we have developed an AI model that is able to look at network packets and network packet data and decide whether or not those packets represent malicious behavior. And the way that we could improve the security process is hand this model off to our security analysts, who can then use it to correlate with the network packet that they're looking at and see what the model's interpretation of that network packet data is, potentially allowing them to focus in on a smaller subset of that data that is more likely to be malicious. In this video, we're going to demonstrate how to integrate a simple AI model with a common security tool. The scenario that we're going to demonstrate is enhancing a traditional file checker with an AI-based file checker. So to get started, let's first look at how our traditional file checker works. For the purposes of this demonstration, I've created a simple Python script that takes as input the name of a file and then returns to you whether or not that file is malicious. Let's see now how that works. I'm going to run it in Windows PowerShell using the command Python, and then I'm going to give it the name of the Python script, which in this case is scanner.py, and then I'm going to give it the name of a file to check. And let's pass it a file called malicious_file.pdf, and then hit enter. And in the output on the terminal, it tells me the file is malicious. Now let's try it with a different file. So I'm going to use the same command, python scanner.py, and then I'm going to pass it a different file. And in the output for unknownfile.csv, it tells me the file is safe to use. So this represents a typical antivirus or file checker program, and it's a very static-based method. And the way that this program works is that it has a database of known signatures or checksums that are associated with malicious files. And when it is passed a new file, it calculates the checksum for that file and compares it against the checksums in its database to see if it's present. If the checksum is present, then it returns the file as malicious, and if the checksum is not present, it returns the file as safe to use. Now this is a good layer of security to have because it has an extremely low false positive rate. If the checksum is found, you can be almost 100% confident that the file is malicious. However, it's also an easy method to evade. In order to evade this file checker, you simply need to tweak your file a little bit to generate an entirely new checksum, and now you can evade the file checker. So what we're going to do is develop a simple AI model that can enhance the traditional security tool and make it a little bit harder to evade that static checksum method. The first thing I'm going to do is activate a Python virtual environment, and then we're going to have to install a few Python packages before we get going. So I'm going to use the command pip install and then pass it the list of packages that we need. This includes matplotlib, numpy, pandas, and scikit-learn. And in this case, my virtual environment already has all of these installed. But if yours doesn't have it installed, then this command will install the necessary packages. So let's get started with a Python interactive session. I'm going to activate that by typing Python and hitting enter. Now let's import the packages that we're going to need. So the first is going to import numpy as np. Then we'll import matplotlib.pyplot as plt. Then we'll import pandas as pd. Then we'll import some of our machine learning libraries. The first will be from sklearn.neighbors import kneighbors classifier. And then from sklearn import metrics. Now we're ready to get started with creating and training our model. So the first thing we're going to do is import our dataset. To do that, I'm going to create a variable called dframe, and then I'm going to use pandas to read a CSV file in. So I'll use pd.read_csv, and I'm going to pass it a file called data.csv. This data.csv file is a fake dataset that I've created representing a collection of various benign and malicious files. So now that we have the data loaded into the data frame, let's take a look at what the data looks like. And I can do that by calling dframe.head. And this outputs the first few records in our dataset. So we can see we have columns going from left to right of file size, title chars, metadata size, number of pages, text, valid header, URI keywords, action keywords, launch keyword, and malicious. Let's talk a little bit more about what these columns are. Again, this is fake data that I've created, but the concepts still apply. And this dataset is specifically aimed at training an AI model to identify malicious PDFs. So a lot of the data in this file and these columns are specifically tuned for malicious indicators of infected PDFs. With that in mind, let's look a little bit closer at what each column represents. The first column, file size, is the overall size of the file. And generally, infected PDFs are going to have a larger file size than normal PDFs. Then we have the number of characters in the title of the file, and longer titles may be indicative of a malicious PDF. Then we have the size of the metadata associated with the file, and once again, larger sizes of metadata may be an indicator that the file is malicious. Next, we have the number of pages in the PDF. Generally, malicious or infected PDFs may have fewer pages associated with them. The next column is the presence of text, as sometimes malicious PDFs may not have any text available in them at all. They will be just blank PDFs. And if we get a blank PDF, that could be an indicator of a malicious file. Then we have a column indicating whether or not the file has a valid header. And if the header file is invalid, it may be a malicious PDF. The next three columns, URI keywords, action keywords, and the launch keyword, are all indicating whether or not various keywords are present in the PDF. These keywords associated with URI, action, and launch are associated with malicious PDFs. And finally, our last column is our label column, and that's the malicious column. So if a file is malicious, it's labeled as 1, and if a file is not malicious, it's labeled as 0. This is what our AI model is going to try to predict. So now that we have an idea of what the data frame consists of and our training data set looks like, let's go ahead and set up our data into a NumPy array so that we can start to work with the training models. First, we'll set up our X variable, which is the data that our AI model will use to predict whether or not a file is malicious. I'll do that by setting the variable X equal to dframe, and then I'm going to pass it the list of columns or features that I want my AI model to predict on. So we're going to use file size, title chars, metadata size, num of pages, text, valid header, URI keywords, action keywords, and launch keyword. Now we want to set up our column of answers, which is going to be the malicious column consisting of our label of malicious or not malicious, and we do that by setting y equals dframe and pass it the malicious column dot values. So let's see what the first few entries in our X array look like, with X open square bracket 0 colon 5 close square bracket. And we can see it looks very similar to our data frame, but we've taken the malicious column out of it. Similarly, we could do Y from 0 to 5, and we have the array of values that we want to predict, or the answers for our model. So now let's go ahead and train the model on our X and Y. To do that, we're going to be using a k-nearest neighbor algorithm. This is a supervised machine learning algorithm, and we use it to perform classification such as malicious and non-malicious based on how close a data point is to other similar data points in the data set. So we'll call our k-nearest neighbors model nay and set it equal to k-neighbors classifier, and then we need to pass it the number of neighbors. For now, we're going to set that variable equal to 4, and then we'll call .fit on that and pass it our X and Y array values. And then we'll hit enter. And now we've trained our model on the X and Y values. Now we've set the number of neighbors nearest to 4. This value is telling our model how many of the nearest points it should look at when classifying a data point. So in this case, our data point will be classified based on the 4 nearest data points to that point. So now let's see our model in action. To do that, we're going to load another CSV file in which I have an entry for an unknown file. So I'm going to call this classify_df and set it equal to pd.read_csv, and I'm going to pass it unknownfile.csv. And this unknownfile.csv is another dataset consisting of only one entry in which I have filled out all of the features of the potential unknown file, but I don't know whether it's malicious or not, so that column is blank. We can see that by once again calling head on classified_df. And we can see the dataset looks very similar, but in the far right in the malicious column, we have not a number, and that's because the value is null. So in this case, we need our newly trained model nay to set this value for us and tell us whether or not this file is malicious based on the values in the feature columns. So now let's once again set that value into a NumPy array. We'll do that by saying classify_x equals classify_df and pass it the feature names, or the column titles, which again is file size, title chars, metadata size, num of pages, text, valid header, URI keywords, action keywords, and launch keyword. Now we can use the AI model that we trained, which we called nay, to predict whether or not this value is malicious. To do that, we'll say y hat equals nay.predict, and we'll pass it this classify x value. And now, if we type in y hat and hit enter, we can see that we have an array and it has one value in it, which is the value that our AI model has predicted as to whether or not this file is malicious. And that value can be seen between the square brackets, which is the value of 1. This indicates that our AI model thinks that this file is malicious based on the feature set that we provided to it. So now we have enhanced the traditional method of checksums by incorporating this AI trained model as well. And the way in which this would be used is not to get rid of the checksum method of protecting our files, but rather to augment that process by also incorporating this AI model to check, because we want to have multiple layers of security and multiple different ways of validating whether or not a file is safe. Now, there are aspects of training the AI model that we didn't look at in this particular scenario, and we'll look at those in an upcoming video. This includes things like evaluating our model for accuracy and setting up training and testing data and splitting it up to help validate our model. In this video, we're going to look at some of the ways that we can interpret the output from an AI model in a security scenario. And note that I'll be starting this demonstration in the same Python interactive session that we were using in the previous video. So on the screen in the terminal, I have the output from the AI model that we made in the previous video. This is the AI model we built that can predict whether or not a file is malicious. So in the example on the screen, I've typed y hat into the terminal, and beneath that we have the output from the AI model. And in this case, the output is an array, and the value inside the square brackets represents what the AI model has determined in terms of whether or not the file is malicious. And since the value on our screen is a 1, that means the AI model in this case has determined the file is malicious. If we had seen a 0 between the square brackets, then we would have a safe-to-use file, or a file that is not malicious. Beside that value, we also have a dtype value. Dtype comes from the NumPy library, and it is a data type object. And in this case, our dtype is set to int64, which is telling us that the values in our array are of type int64. So this is what we see at the surface level in terms of output from our AI model, but we can go deeper than that. Oftentimes, there are other aspects to our output that we want to see. An example of this could be the accuracy score of our AI model, which will tell us how accurate this prediction from the AI model is. There are a number of different ways that we can evaluate the accuracy from an AI model, so it's important to ensure that whatever accuracy score method you choose makes sense for the model that you've built. In this case, we're going to use the Jacquard score function, and to do that, we're going to use metrics from sklearn. So following on from the previous video, we'll need to make sure that we have the scikit-learn library installed, and we'll have to import it into our Python session. So to get the metrics library imported, we use the command from sklearn import metrics. And in order to properly evaluate our accuracy, we're going to have to split our data up into a training set and a testing set, something we didn't do in the previous video. Previously with our model, we just used the entire data set as our training set and then immediately went on to an unknown file as a prediction. In this case, we're going to have to take our data set and split it up. To do that, we're going to import another library from sklearn.model_selection import train test split. And now we'll use the x and y values from our previous demonstration, with x being the feature set that our AI model uses to make predictions on, and y being the answer set that our AI model is trying to achieve. And we're going to split them up into xtrain, xtest, ytrain, and ytest. And we set those equal to train test split, and then we pass the x and the y values into that function. In this case, we'll give it a test size of 0.2, which means that it's going to split up our data set as 20% test and 80% trained. And then we need to give it a random state, which we'll give it as 4, which will set the seed for the random number generator in the train test split library. This will make it so that the way in which our dataset is split into testing sets and training sets is deterministic, and our training set and testing set will be the same every time, regardless of how many times we run this command. So now we have our overall datasets split up into training and testing sets, whereas before we trained the model solely on the x and y values as a whole. So now we'll need to retrain our AI model on the training set. Remember, previously we called our AI model Nay, so we're going to reassign Nay and set it equal to k_neighbors classifier. And we're going to pass it the number of neighbors to use, and we'll use 4 again. and we'll fit it on the training set this time, X-train and Y-train. Now we're ready to get some metrics on how accurate our AI model is. So first, let's get our training set accuracy. And we can do that by calling metrics.accuracyscore, and we're going to pass it the Y training set, and then we're going to pass it the values that the AI model predicts on the X training set. So we'll pass it nay.predictXtrain. And in this case, we have an accuracy of 1, which means our AI model is perfect. However, this should immediately raise some red flags because with the minimal amount of effort that we put into training this AI model in this case, we should not have such a good accuracy score. Now, the reason we have a high accuracy score in this case is because the dataset was entirely created and curated by me to be a perfectly split dataset. There is no ambiguity in the dataset, so the AI model can make perfect predictions. With a real-world dataset, you'd have a lot more ambiguity and some overlap in the data. Now, we will also want to see the accuracy in terms of how our AI model performs on the testing set. So to do that, we're going to get a full prediction of the testing set by setting y hat equal to nay.predict, and then pass it xtest. So now our AI model has created a prediction of what it thinks all of the answers for the testing set should be. And once again, we can call metrics.accuracyscore, and then pass it ytest and y hat, and hit enter. And once again, we have a perfect accuracy as a result of having a perfectly curated dataset. So these accuracy values are where you would go to see whether or not your AI model meets your required threshold for proper accuracy in order to trust the results. Every use case will have a different tolerance for how accurate the results can be. With the more mission critical your process is, the higher the accuracy required will be. But it's important not to just take the output of the AI model at face value. You'll want to dig deeper and understand how accurate that output is actually going to be and how much you can rely on that output. In this video, we're going to compare a traditional security tool and an AI-enhanced security tool when handling the same threat. So for the purposes of this demonstration, the traditional security tool that we will be looking at is our file scanner that we created previously as part of the demonstration in video 11, and the AI-enhanced security tool will be the AI model that we created in that same video. As a reminder, let's first see how the traditional security tool works. We call Python scanner.py, with scanner.py being the name of the security tool, and then we pass it a file to check. So for example, we could pass it maliciousPDF.pdf. And as you might guess, malicious PDF is an infected PDF, and our file scanner should pick up on that. And when I hit enter, the output indicates that the file is malicious. So this is working as intended. Now let's see how this traditional tool handles a new and unknown threat. So once again, I'm going to call Python scanner.py, and I've passed it this file name, which consists of a long string of random characters with .pdf at the end. So let's pretend that this file was alerted to us because it came in a potentially suspicious email, and now we as a security analyst want to investigate it ourselves. The first red flag is the file name. Clearly something is wrong. Generally, files aren't named like this, so we would be immediately suspicious of this file. But I'm going to put it through my scanner tool and see what happens. And my scanner has told me that the file is safe to use. So in this case, if we relied solely on the traditional file scanner, which as a reminder again, works by comparing the checksum of a file to a known database of checksums or signatures of malicious files, and then checks whether or not the checksum is in that database, and if it is, the file is classified as malicious, and if it's not, the file is classified as safe. So if we went just on the output of this traditional security tool, we would now be under the impression that this PDF is safe to view and safe to open. However, I know for a fact that this is an infected PDF. This file is actually malicious. So if we were to open this file, we would launch a virus or some sort of malware onto our system. So unfortunately, in this case, our traditional security tool has failed us. Now, that's not to say that this traditional security tool could never handle this threat. Let's pretend that down the line we get some new threat intelligence, and we've now discovered that this file is malicious. Unfortunately, at this point, the damage has already been done, the PDF has been opened, but we want to make sure that we're protected from the threat going forward. So with a traditional security tool, we would now have to perform a signature database update. To do that, we're going to have to first get the file hash of the infected file. In a PowerShell window, we can get that checksum using the command getFileHash, and then pass the name of the file to that command, followed by -algorithm, and then the name of the algorithm that we want to use, in this case SHA-256. And the output of that command gives us the SHA-256 checksum for our malicious file. It can be seen under the hash column in the output. So now we are going to update our signature database to include this checksum. So now on the screen in the Notepad window, I have our signatures database. This is a fairly minimal database in that it is just a text file of signatures, but it works for our purposes. And in this case, we can see that we only have one entry currently, and that's the checksum of the file that was previously indicated to be malicious. So now we're going to add a new line, and we're going to paste in the checksum of the newly discovered malicious file. So now I've updated our signature database. Let's return to our traditional security tool and see how it handles the malicious file now. So I'm going to use that same command, python scanner.py, and pass in the file name of the malicious file. And now it tells us the file is malicious. So as a result of our signature database update, our scanner now catches this malicious file. However, you can see how this would be a tedious task and requires making sure that your signature database is continually up to date. And no matter how up to date your signature database is, any new and emerging threat is always going to bypass your signature checking because the threat intelligence will not have caught up yet with that new threat. So while our traditional security tool has been able to eventually handle this threat, let's see how an AI-enhanced security tool will handle this threat on day one. So now on the screen, in this PowerShell window, I'm back in the same Python interactive terminal session that I've been using for the previous two demonstrations. This terminal has our trained AI model ready to handle and predict whether or not files are malicious. So we've trained this model on a known dataset of malicious and benign PDFs, and we can use it to tell whether or not a new PDF is malicious. In order to perform a prediction on this new file, we first need to get the information about the file into our model. Luckily, our security analysts have already done this for us and extracted the information about the file and put it into a CSV. So we can read that CSV into our interactive session, and we'll call it predict_df. And we'll set that equal to pd.readCSV. And remember, pd is the pandas library, and we'll pass it new pdf_info.csv. Now we're going to translate that data frame into a NumPy array, and we'll do that using this command. We'll set a variable called predictx equal to all of the various columns in our predict data frame. In this case, it's file size, title chars, metadata size, number of pages, text, valid header, URI keywords, action keywords, and launch keyword. And we can look at what each of these values are if we call head on the predict data frame. And so these would be the values that our security analysts have extracted for us to put into the model for the potentially malicious file. We have a file size of 31 megabytes. The number of characters in the title is 73. Our metadata size is 7,692 kilobytes. The number of pages in our PDF is 1. There is no text present in our PDF. The PDF does not have a valid header, and there are no keywords associated with URI, action, or launch. So now, based on this data, we're going to use our AI model to predict whether or not this file is malicious. So the AI model, in our previous demonstration, we called nay, and we'll call .predict on that model, and then we'll pass it our predictx, and we'll set all of that equal to y hat. And now we can check the value of y hat, and the output of whether or not the file is malicious can be seen between the square brackets in the output beside array. And in this case, it's a value of 1, indicating that the file is malicious. So in this case, our AI-enhanced model would have detected that the file is malicious on day 1, as opposed to having to wait for the signature database to be updated before it can be detected as malicious. So this shows one of the differences between a traditional security tool and an AI-enhanced security tool. In this video, we're going to look at some common issues that might pop up when you're working with AI tools, and look at how we can troubleshoot those issues. To do this, we're going to be working with the same AI model that we've been working with in the previous demonstrations. So on the screen, we have a Python interactive session, and I've recreated the steps to create and train our model in the same way that we've seen previously. So I've imported the necessary libraries, and then going line by line from the top, in the first line, we've read scrambled data.csv into a pandas data frame. Previously, we used a file called data.csv, and this was a fake data set created by me and perfectly curated for a machine learning algorithm to have 100% accuracy in its predictions. With scrambled data.csv, it's the same dataset structure, but now I've set it up so that it does not have this perfectly curated nature, and we're going to see how that affects our AI model's predictions. Below that line, I've called head on dframe just so that we can see the first few lines of the scrambled data file and see that they are the same as we saw previously, with the feature set being file size, title chars, metadata size, number of pages, text, valid header, URI keywords, action keywords, and launch keyword, and the value that we want to predict being the malicious column, with 0 being not malicious and 1 being malicious. Below that, I've translated our feature set into a NumPy array with all of the relevant features assigned into the X value, and then we've also assigned the Y value to be the values in the malicious column. And then I've used the train test split method in the sklearn library to create a training and test set on which we can train and test our model. Below that, I've set a k value of 1, which represents the number of neighbors that we're going to be using in our k nearest neighbors algorithm, and we'll come back to that value later. Then I've created the model and called it model, and I've trained it on the xtrain and ytrain dataset using the k neighbors classifier algorithm and passing it our k value as the number of neighbors. Finally, I've created y-hat as the predicted answer values using the x test set and the AI model to predict based on that test set. So now we are ready to look at some issues that might have popped up as a result of using this tool and training it in this way. First, let's see what the first few values of y-hat are and see what our model has predicted. To do that, I've called y-hat open bracket 0:5 close bracket, and this gives us the first 5 answers in y-hat. And so inside the array brackets, we have the values 0, 0, 0, 0, and 1. This means the first 4 predictions have labeled the file as not malicious, and the 5th prediction has labeled the file as malicious. So now let's see what our accuracy level is in terms of how much can we trust these values. So I'm going to use the metrics library from sklearn again, and we're going to get the accuracy score in terms of how accurate our AI model did or how well it performed on the test set. To do that, I'm going to call metrics.accuracyscore, and I'm going to pass it ytest and y-hat, with ytest being the known answers and y-hat representing the answers that the AI model came up with. And we can see that we have an accuracy score of 0.525. This is significantly decreased from our previous accuracy score on the perfect dataset of 100%. So we can see that we have about a 50-50 ratio in terms of getting the answer right. Now this is not very good, as it's pretty similar to doing a coin flip on whether or not a file is malicious. Generally, if we're relying on this for security purposes, we're going to want to get this accuracy score significantly higher. So this is the first issue that you're going to run into pretty frequently with any AI model. You're going to find that the accuracy score is often not sufficient for your use case. And in order to improve this accuracy score, you're going to have to tweak the way in which you train the model somehow. Now the first thing we could do is look at our dataset. And in this case, there's definitely room for us to improve our dataset. Since I've just created a completely random dataset, it's not necessarily representative of real-world patterns. So it's very possible that the way in which we've trained the model would actually perform better on a real-world dataset as opposed to my completely random dataset. Next, we can also look at the different parameters that we've used to train the model. Every algorithm is going to have different parameters that you can use in order to tweak the training. So we're going to focus just on the k nearest neighbors algorithm in this case to show the theory behind tweaking the parameters. With the k nearest neighbors, the most important parameter is going to be our k value, or the number of nearest points that we compare any given point to. In our AI model in this case, we used a k value of 1. This means that we're only comparing each data point to one other data point. Very likely, this k value is far too low. So what we could do is retrain our model with a higher k value, something like 5, and see how our accuracy score changes. So let's do that now. I'll set k equal to 5, and then I'm going to retrain the model again on the same training set, but with this higher number of neighbors. Now, we need to use the model to once again predict our y-hat values, which we do by calling y-hat equals model.predict on the x test set. And then we can call the metrics.accuracyscore again on this new y-hat and see how our accuracy has changed. Now, given that this is an entirely random dataset, it's very possible that our accuracy score in this case could actually decrease. But in general, increasing the number of neighbors from 1 up to 5 should usually improve this algorithm. However, that trend won't continue infinitely. A higher number of neighbors will not always translate into better accuracy. At some point, there is going to be the right number of neighbors, beyond which increasing the number actually decreases the effectiveness of your model. And lo and behold, in this case, Our output now with the metric's accuracy score is still 0.52, so we haven't really increased our accuracy score. Now, this kind of makes sense conceptually if you think about it, because since the dataset is completely random, there are no patterns for the AI model to pick up on. So sitting around a coin flip is about what we would expect in this case. But when deciding on what k-value to use, in terms of the number of neighbors, we can do a little bit better than just randomly plopping in a value and hoping it improves. One possible way is by looking at a plot of many different k-values and seeing how our accuracy changes. So to do this, we'll first decide on what range of k-values we want to look at. And let's arbitrarily pick 20. And we're going to create a numpy array filled with zeros for our average accuracy. And I create that numpy array by calling np.zeros and passing it the total number that we want to pick, minus 1, and assigning it to average accuracy. So I can see what average accuracy looks like right now, and it's an array of all zeros. Now we're going to loop with for I in range from 1 up to our total number that we want to use. And for each value, we're going to train the model on that value, then create our y-hat predictions, and see what our accuracy score is, and save that into our average accuracy array. And now we can look at our average accuracy array again, and we can see that it is filled with values, these values representing the accuracy at each given neighbor. With our random data set, we don't have a huge variation, running from about 0.52 down to about 0.48. But again, with a real-world set, you would probably see a much wider variance in terms of the accuracy values for each neighbor value. A good way that we can visualize this is by using a plot. This is where we're going to bring in matplotlib, which we imported in previous demonstrations as plt. So to do this, we'll call plt.plot, and we'll pass it a range from 1 up to our total number of k's. And then we'll pass it our average accuracy array and a value of g to show our values in green. And let's see what that plot looks like by calling plt.show. And here we have a very basic visualization of our accuracy. Along the y-axis, we have the accuracy value, and along the x-axis, we have the number of neighbors. And this very quickly tells us that a number of neighbors value of 13 is going to give us our highest accuracy in this case. So this is one of the ways that we can go about troubleshooting one of the most common issues that we're going to see with AI models. In this video, we're going to demonstrate how an AI model can be used for identity verification. To do this, we're going to be creating our facial recognition AI model using Python and some of its associated libraries. So to get started, we first need to make sure that we have the necessary Python libraries installed. On my screen, I have a Windows PowerShell terminal running with a Python virtual environment. And so to install the libraries that we need, I'm going to use the command pip3 install, and we're going to install face recognition and hit enter. And in my case, I already have the face recognition library installed, but if you didn't have it, this command would install the library for you. So at this point, we're ready to start creating the Python script to do the facial recognition. So on my screen, I've opened up a Notepad++ window, which is where we're going to be creating the code for our Python script. And we've called our Python script faceauthenticator.py. So the way that this script is going to be set up to work is that it's going to take in a command line argument representing the image that we want to check, and it's going to compare that image against a known image already loaded in its library to see whether or not that image is a sufficient match to the image already in our library to allow authentication into our system. So first, let's import the face recognition library with the line import face recognition. And now we're going to set up the baseline image against which the user is trying to authenticate. And in terms of sourcing the images, we've used this labeled faces in the wild database, the URL for which can be seen at the top of my screen in the bar at https://vis-www.cs.umass.edu/lfw. And on this page, we can scroll down until we see Explore the Database. And if we click on W and we search for Wayne Gretzky, we can see the 4 images that we have available to us for Wayne Gretzky. Similarly, if we go back to the Explore the Database page and we click on M, we can search for Mario Lemieux, and we have the image of Mario Lemieux. So these are two hockey players that we're going to be using for our system test. So in this situation, we are going to assume that Wayne Gretzky is a user in the system, and only Wayne Gretzky's face should be allowed to authenticate to our system. And so we'll create a variable called Gretzky face, and we're going to set that equal to face recognition.load image file. And as an argument, we're going to pass it a string to the location of the Wayne Gretzky image. In this case, we have the Wayne Gretzky image stored in the same directory from which the script is going to be run, and it's called waynegretzky1.jpg. And so now we have the face that we're going to compare against when authenticating to our system. Now we need to encode that face image in order to use it within the library. So we're going to create Gretzky face encoding as a variable, and set it equal to face recognition.face encodings. And as an argument, we'll pass it the Gretzky face variable. And we want our Gretzky face encoding to be the first element in the returned list. Next, we need to load in the image that we're going to compare against this file. Since this image is going to be passed on the command line, we're going to grab it using sys.argv. So I'm going to go back up to the top and import another library underneath face recognition, and it's going to be import sys. And so now we're going to create a new variable called unknown face, and we're going to set it equal to face recognition.load image file. And we're going to pass it sys.argv, and in brackets the number 1, which will insert the first argument passed to our script. In a production system, you would want to do a lot more safety checks here before using the argument on the command line to directly load the image file. But for our purposes, this is going to work okay. And now we're going to encode the unknown face in the same way that we did previously. So we'll create a variable called unknown face encoding. And set it equal to face recognition.face encodings. And we'll pass it the unknown face variable. And once again, we want to get the first element in the list. Now we are going to calculate the distance between the two images, which is going to represent how similar the images are. And to do that, we'll create a variable called face distance and set it equal to face recognition.face distance. And then the first argument to this function is going to be a list of the known encodings. In this case, we only have one, the Gretzky face encoding. And the second argument will be the face that we want to compare against, in this case, unknown face encoding. And now at this point, we are going to need to establish the face distance at which we would want to cut off authenticating versus denying authentication. So let's start out by just printing out this face distance and seeing what kind of values we get with different images fed into the system. And so I've just added a print statement to print that face distance variable out to give us a little bit of information about what we're going to be seeing. So I'm going to return to my Windows PowerShell terminal, and I'm going to run this new Python script using the command python face authenticator.py, and as an argument, I'm going to pass it a second image of Wayne Gretzky that's different than the first, and that's called waynegretzky2.jpg. And then I'm going to hit enter, and it output the face distance between the two images, which is 0.37828.725. And for reference, here are the two images that we compared, with Wayne Gretzky 1, our base image, being on the left, and Wayne Gretzky 2, the image in which we were testing, on the right. Now let's try it again, but in this case, we're going to be comparing the image of Mario Lemieux to our library image of Wayne Gretzky. And that image of Mario Lemieux is on the screen on the right. And we'll see what kind of face distance we get with this image. So I'm going to use the same command, python faceauthenticator.py, but I'm going to pass it the image of Mario Lemieux instead. And it has output a face distance of 0.65755654. So what we can see is that the more similar a face image is, the lower that face distance is going to be. So we need to establish a cutoff somewhere in terms of where that authentication is going to allow authentication versus deny authentication. And it seems like a good value is 0.6. So I'm going to return to our script, and I'm going to delete this print statement. And now I'm going to add a conditional. And that conditional is going to say if face distance is less than 0.6, we're going to print out authentication allowed. And this is where in a production system, if this check passed, you would grant the user an authentication token or somehow allow the user into your system. Then I'm going to add an else statement. And if the face distance is not less than 0.6, I'm going to print out authentication denied. So now let's return to our terminal and try these commands again. So I'm going to rerun the first command with the Wayne Gretzky 2 image, and it prints out that authentication has been allowed. Next, I'm going to try the Mario Lemieux image again, and we can see that authentication has been denied. Let's try it again with the third Wayne Gretzky image, which we haven't tried yet in our system. And that one's called WayneGretzky3.jpg. And that authentication has been allowed as well. And once again, for reference, here is the Wayne Gretzky library image that we're using on the left, and here is Wayne Gretzky 3, the third image that we just tried, on the right. So this is one way in which we can use AI models to perform identity verification. In this video, we're going to look at a comparison of an AI-powered identity verification method versus a more traditional identity verification method. And then we'll also take a look at how they can be used to complement each other. So for our AI-powered identity verification method, we're going to be using the face authenticator script that we created in the previous video. As a quick recap, this face authenticator script works by storing a known face into its library, in this case a picture of Wayne Gretzky's face, and then comparing that library face with a face that's passed in as a command line argument to the script, representing a user trying to authenticate into the system. If the distance between the faces is less than 0.6, the authentication will be allowed, and otherwise the authentication will be denied. And as a refresher, to see this AI-powered identity verification method in action, we can call python faceauthenticator.py and pass in a picture of Wayne Gretzky to the script, and it returns to us that authentication is allowed. Similarly, we could pass in a picture of Mario Lemieux, and our authentication is denied. So this is an AI-powered identity verification method. We are using a trained model to recognize and detect features of a known face, and then using that same AI model to detect and recognize features of an unknown face and compare the two in order to get a similarity metric. Now, let's create a new Python script that will represent a more traditional identity verification method, in this case, a username and password. So I've opened up a Notepad++ window, and in this window, we're going to create a simple script that uses a username and password to check whether or not a user is authenticated to a system. Now, as with the previous video, this is going to be a proof of concept system, so it's going to use hard-coded credentials to check against, and it's going to be lacking a lot of crucial safety and robustness features, and would not be a suitable way to implement this authentication in a production system. So with that in mind, let's get started with creating the script. We'll start by hard-coding a username and password into our system. So first, I define a username variable, and I set it equal to the string w_Gretzky. And then I create a password variable, and I set it equal to password1. These are the credentials that we'll be checking when a user authenticates into the system. As with Face Authenticator, we're going to be using command line arguments, so we're going to need the sys library. So at the top of this script, I'm going to import sys. We'll set it up so that the first argument is the username, and the second argument is the password that the user has entered. So I set a variable called entered username equal to sys.argv at the index of 1, which will get the first argument passed to the script. And then I create another variable called entered password, and I set that equal to sys.argv at the index of 2, which will get the second argument passed into the script. Now we can create a conditional to say if entered username equals the username in our hard-coded script and entered password equals the password associated with that username, authentication will be granted, and otherwise authentication will be denied. So I type if username equals entered username and password equals entered password, we print authentication successful, else we'll print authentication denied. So now let's see this traditional script in action. We use the command python, and now we call the new script, which is called traditionalauthenticator.py, and we're going to pass it w_Gretzky and password1. And when I hit enter, it tells me authentication was successful because the username and password matched. However, if I changed one of them to not match, for example, I give it w_Gretzky and password2, it tells me authentication denied. This is the traditional authentication method that many of us are very familiar with. So let's summarize some of the comparisons between our AI-powered facial recognition authenticator and our more traditional password-based authenticator. With our password-based authenticator, there's no intelligence behind the system. We are comparing a given set of credentials to a stored set of credentials, and if those credentials match, then we allow access, and if they don't, we deny access. In terms of weaknesses with this system, we have a few vulnerabilities or weaknesses that can occur. First, this type of setup is reliant on users making secure passwords and not having those passwords be compromised. So if our users create weak passwords like password1, then it is very easy for a malicious actor to break into their account and perform harmful actions. Similarly, if a user does not practice good password hygiene, for example, they reuse their password across multiple websites, then it's more likely for that password to become compromised, and once one account is compromised, all the other accounts using the same password are also compromised. With the AI-powered facial recognition system, we don't have those same vulnerabilities. We're not reliant on the user creating a password to set the level of security. The user doesn't need to remember anything, they just need to register their face so that the AI model can then use it as a comparison basis. So it takes the onus off of the end user to set the level of security with their authentication and puts the onus on the AI model to set the level of security. This doesn't mean that the facial authentication system is immune to all vulnerabilities or weaknesses, but it changes whose responsibility it is to provide the security, and it's far preferable to put the responsibility of establishing security into the hands of experts. With all of that said, these two systems do not need to be exclusive. We can actually use them together to complement each other and add multiple layers of security on top of each other in order to mitigate the weaknesses of both and maximize the strengths of both. This is the idea behind multi-factor authentication, and combining traditional security and authentication methods with AI-powered ones is a very powerful combination to bring forward. So to see this in action, let's combine this traditional authentication script that we just created with the facial recognition script that we created in the previous video. So I'm going to copy all of this code, and then I'm going to change tabs to our facial authentication script, and before the final conditional, I'm going to paste in the traditional authentication script that we just created. And so now, in our script, we have the code for the facial recognition and the code for the traditional authentication, and then at the bottom of the script, we have the two conditionals used for each script. At this point, we're going to combine the conditionals into one conditional, so I'm going to copy the logic of if username is equal to entered username and password is equal to entered password, and combine it into the face distance less than 0.6 conditional. So now our ending conditional reads like if the facial distance is less than 0.6 and both the username and password that has been entered equal the username and password in our database, we will allow access. If any of these conditions fail, we will deny access. So we are now relying on both facial recognition and password authentication to create our multi-factor authentication system. We also need to do one more modification and change the index for the entered username to be 2 and the entered password to be 3. This is because our first argument is going to be the image, which we use to authenticate, and our second and third arguments will now be the username and password. So now we can run our enhanced multi-factor authentication system with the command Python face authenticator, and we're going to pass it the picture of Wayne Gretzky 3, followed by the username W_Gretzky and the password password1. And the output is that authentication is allowed. Now let's try it again with the password of password2. And in this case, authentication has been denied. Finally, let's try it with the correct username and password, but we're going to change the picture to Mario Lemieux's picture. So in this case, we can pretend like the username and password has been compromised, but the attacker still needs to use their face to authenticate to the system. And in this case, even though the username and password has been compromised and the attacker has the correct credentials, the authentication has been denied because their facial recognition does not match. So this represents a comparison between the two systems and shows how they can work together. In this video, we're going to use AI to detect potential identity threats. To do this, we're going to use the same facial recognition identity verification system that we created in the previous videos. As a quick recap, this system works by learning a known face and then comparing any entered faces by the username against that known face and checking for similarity metrics to determine whether or not the face is a close enough match to allow authentication. We then augmented this system to implement a multi-factor method by combining it with a username and password authentication system so that any user needs to both have the correct face and the correct credentials to access the system. So now we're going to once again build up this same system by incorporating an AI alert system when it detects a potential threat. For the purposes of this demonstration, we're going to set up a scenario. And our scenario is that we have obtained threat intelligence telling us that there are malicious actors trying to access our system, and they are likely going to be using pictures of known celebrities to try and bypass our facial recognition system. And our threat intelligence goes even further to tell us that specifically they use pictures of Serena Williams, the famous tennis player, to try and bypass facial recognition systems. With this threat intel in hand, we are going to incorporate an alert system into our facial authentication identity verification method to raise an alert to our security analysts whenever we detect that something matching our threat intelligence report has been entered into our system. So first, I'm going to consolidate the existing code that we've already created a little bit by removing the white space between the lines. And now I'm going to add a new code block which will represent our AI-powered threat detection block. So given that our threat intelligence tells us that malicious actors are trying to use Serena Williams' face to bypass our system, we are going to encode Serena Williams' face into our AI model. So I'll create a variable called Williams face, and I'm going to set it equal to face recognition.load image file. And I'm going to pass it the path to the picture of Serena Williams, which is in the same directory as this script, and it's serenawilliams1.jpg. And then I'm going to create an encoding of that variable and call it Williams face encoding, and set that equal to face recognition.faceEncodings. And I'll pass it Williams face. And I want the first index in that list. Now we are going to compare any face that's input into our system against this known Serena Williams face to detect whether or not a malicious actor might be trying to bypass our facial recognition system. So I'll make a new variable called threatIntelResult, and I'm going to set it equal to faceRecognition.compareFaces. And the first argument I'm going to give this function is the list of faces to compare against. In this case, we only have one, which is the Williams face encoding. And the second argument will be the face that has been passed in by the user, in this case, unknown face encoding. Now, threat intel result will be an array containing the results of whether or not the AI model has detected that the entered face is the face of Serena Williams or not. And so I can check if threat intel result at 0, then we'll raise an alert. And in this case, if the threat intelligence result is true, we're going to exit the Python script and raise an alert saying potential attack as per threat intelligence. So now we'll return to our PowerShell terminal and try this out. We'll start with a successful authentication once again by calling Python faceauthenticator.py, passing it the picture of Wayne Gretzky, the username of W_Gretzky, and the password of password1. And our authentication is allowed. Now, let's try passing it our picture of Serena Williams to see how our threat intelligence handles that case. And, as we can see in the output, it tells us potential attack as per threat intelligence. And in this case, our AI model has detected a potential threat, it has exited the system, it has not allowed authentication, and it has raised an alert to our security analyst. So this is an example of how AI can be used to prevent identity theft and protect our systems. Now, in this case, we built our threat intelligence off of a very specific scenario that we built up. In reality, you would not train your AI-powered threat intelligence to focus on just one face and raise an alert based on that. Rather, you would have a huge database of things like known celebrity faces and AI-generated faces and other things that would raise red flags and alert based on that rather than a statically hard-coded face. This would give you a much more effective alert system, but the overall principle is still the same. We want to build up a database of anything that is indicative of a threat to us, and we can get that threat intelligence report from a variety of different sources and use that to continually train and build up our AI model to have the best alerting system that we possibly can. And it's important that we incorporate any new tactics, techniques, and procedures that we learn that are being used by malicious actors into our AI model as we learn them. In this video, we're going to demonstrate how an AI model can be used to detect spam and phishing emails and enhance our overall predictive capabilities. To do this, we're going to be building our AI model using Python and the scikit-learn library. So to get started, first let's open up a PowerShell window, and in the terminal, we're going to install some dependencies that we need for our AI model. So we're going to use the command pip3 install, and the two libraries that we're going to install are pandas and scikit-learn. And in my case, I already have these libraries installed, but if you didn't have these libraries installed, this command would install them for you. The next step is to obtain a dataset that we're going to use to train our AI model on. And the dataset that we're going to be using can be found at the URL seen at the top of my screen, which is https://github.com/small-lion/python-projects/main/spam detection/spam.csv. And then on this page, in the middle near the right side, there's a download raw file button, and if we click on that, we'll get the CSV file that we can use to train our AI model. Taking a quick look at the contents of this file, we can see it consists of two columns. The first column, titled V1, is the classification result of a particular email. And in this case, if it says ham, the email is not a spam email, and if it's classified as spam, the email is a spam email. And then in the second column, titled V2, we have the actual text of the email. So we're going to be using the email contents in this case to train our AI model. There are many different ways that you can go about training models to detect spam emails, and you could be using things like metadata, volume, time, and much more. In this case, we're going to stick to training our model on just the email contents themselves. So now let's return to our PowerShell terminal, and we're going to start up Python with the command python. Now we have an interactive session where we're going to start building our model. First, let's import our libraries. We're going to do import pandas as PD, and then we're going to import some modules from sklearn. The first is from sklearn.model_selection import train test split. Next, we're going to do from sklearn.featureextraction.text import count vectorizer. And finally, we'll do from sklearn import svm. And we'll talk more about what each of these modules are doing as we get to using them. The first step is to use pandas to read our spam CSV file that we downloaded into a data frame. And this data frame is going to put our data into a convenient format to work with when training our model. So we'll call the variable dataset and set it equal to pd.read_CSV and give it the name of the file, in this case spam.csv. Now in my case, the spam.csv file is located in the same folder that I'm running the interactive session from. But if it was not, you would have to provide the full path to the file here. So now we have our information into a dataset. Let's take a quick look at what that dataset looks like. First, we'll call dataset.columns. And we can see that we have the columns that we expect to see, with V1 and V2 representing the classification and the email text contents respectively. There are also some empty columns unnamed 2, 3, and 4 on the right, but we can ignore those. We could also take a look at what the dataset looks like by looking at the first few records by calling dataset.head. And in this case, we can see some of the first records that are input in our dataset. So now let's load the contents of the email into our x variable, which is going to represent the feature set that we are training our model on. So we set x equal to dataset at v2, and then we'll set up a y variable, which will be the prediction that we want to make, or the classification that we're going to classify our emails as. And we'll set that equal to dataset at v1. Now we're going to use the first sklearn module that we imported, train test split. Train test split lets us split up our dataset into training sets and testing sets. In this way, we can train our model on a subset of the data and then test our model on another subset of the data to see how accurate or how well it is performing. So we need to define 4 variables, and in this case it's going to be xtrain, xtest, ytrain, and ytest, and we're going to set that all equal to train test split. We'll pass it x and y, and then we need to give it a test size. The test size represents what percentage of the data we want to be our test data and what percentage of the data we want to be our trained data. In this case, we're going to set our test size equal to 0.2. So a test size of 0.2 means that the test dataset will represent 20% of our overall dataset, with the remaining 80% being our training set. Now, we need to start thinking about how we want to use the contents of the email in order to predict whether or not that email is spam. And in this case, one possible approach we could do is by counting the reoccurrence of words in the email. So by having our model look at the frequency of words and how often those particular words might be associated with spam emails, we could get a good predictor of whether or not an email is spam or not. This is where we're going to use the count vectorizer module that we imported earlier. So first, we need to instantiate an instance of the count vectorizer class, and we'll call it word counter, which we set equal to count vectorizer. The way that count vectorizer works is that it will give every word in a given string a number and then count how many times that word occurs in the string and store that count for us. Ultimately, this represents the actual feature set that we're going to be training our model on. So we're going to make another variable called features and set it equal to word counter dot fit underscore transform, and we're going to pass it xtrain, which is the training portion of our dataset. And we can take a look at what count vectorizer has done for us if we print out the features variable. And here we see the output of features. If we look at the first line, which I've highlighted at the top of the screen, we'll go through what we're actually seeing here. Inside the round brackets, we have 2 values. The first value, 0, is the index of the particular feature or record that we're looking at. The second number, in this case 4031, is the number that count vectorizer has assigned to a given word in that record. And then finally, outside of the round brackets on the right side of the line, we have the number 1. This is the amount of times that word has occurred. And so count vectorizer has done this for all of our training set, and now we can go ahead and start creating our model with this. To do that, we're going to create an SVM model. which was the third module that we imported. So we'll call our model spam predictor and set it equal to svm.svc. And in this case, SVM stands for support vector machine, and SVC stands for support vector classifier. At a high level, this is creating a classification model for us. So now we'll fit the model by calling spampredictor.fit, and we're going to pass it the features that we created and ytrain, which represents the known answers to our training set. So at this point, we have now trained our spam predictor to potentially predict whether an email is spam or not based on the word count frequency within an email's contents. Our next step is to actually test our model. So let's create another variable called spam predictor test. And then we're going to once again make use of our count vectorizer by setting it equal to word counter.transform and passing it xtest. So now if I print spam predictor test, we can see that this has performed the same thing that we did to get our previous feature set, except that now we're using our testing subset instead of our training subset. And now we'll see how our spam predictor performs on this spam predictor test set. So we'll call spam predictor dot score. We'll pass it the spam predictor test set. And we'll give it the known answers so it can compare by passing it ytest. And then the output of our score is 0.98, meaning that we have an accuracy score of 98%, which is a decent score in this case. So now at this point, we have an AI model trained to identify spam emails based on the contents of the text in those emails. In this video, we're going to look at some of the traditional email security measures and techniques we can take to identify spam and phishing emails, and then compare those techniques against our AI-powered model designed to detect and identify spam emails. To start, let's look at some traditional email security measures. Now, the first traditional security measure is generally done behind the scenes for you by any email provider, and this is the automatic classification of an email into spam. So sometimes when you get an email, your email system will filter it automatically and place it into a spam folder. This is generally the first line of defense against emails. However, let's assume that the email has gotten through the spam filter and ended up in our inbox. And so on our screen right now is an example of an email that may have made it through the spam filter, and we now need to determine whether or not this email is legitimate or if it is a potential spam or phishing email. And so we have a variety of ways that we can do this available to us. The first thing we can do is use our own cybersecurity knowledge and our knowledge of how spam emails work and how phishing emails work to examine whether or not this email looks suspicious using our own intuition. So when we look at the text of this email, the first thing we notice is a sense of urgency. The text starts out with winner in capitals with exclamation points, and it says at the end that the offer is valid only for 12 hours. And then we have some sort of incentive, incentivizing us to call a number because we've won a monetary reward. So right off the bat, we can see that there is some suspicion coming into play. We know that spam emails try to create a sense of urgency, and they try to create a time frame in which we need to do something. And we can also see a few grammatical mistakes, like there is a missing space between the word receive and the word a. And then we have the word a and another a with a symbol above it. And so we have this unnecessarily repeating word. All of these are big red flags and are indicative that this is a spam or phishing email. Now, also, we can look at the origin of the email. This is coming from test, and we see it's coming from test@test.com. So we can do a few things with this email address. We could go and test it on a known database of spam emails and find out whether or not this is flagged as a suspicious email. There are a variety of online services that can perform this for you, and one such example is on the screen now. In my browser, I've gone to the URL cleantalk.org/blacklists, and here I'm going to put in test@test.com to see what kind of reports I've seen for this email. And it tells me that test@test.com has been reported as spam. So this is another indicator that we have a malicious email of some sort on our hands. We could go even deeper than this and find out the source IP address that the email was sent from, and also check it in this blacklist as well. And so we can do that in this case by going to our email, and the exact specifics of where these buttons are located will vary based on email service that you're using. But in this case with Thunderbird, we click on More in the top right, and we then click View Source. And here we can get other kinds of metadata information about the email that was sent, all of which could be useful for detecting whether or not this email is suspicious. Now we can go deeper still, but at this point we have a pretty good idea that we're dealing with a spam or phishing email. However, in this case it was very obvious. Sometimes it may be more subtle and harder to detect, in which case you may be more likely to miss the red flags, or it will take you that much longer to identify it. So we can already see some issues with the techniques that we've done. First, this is very time consuming. It can take us quite a while to identify a single email, and spam and phishing emails come in at a very high volume. So if you were trying to perform this procedure on every email yourself, you would quickly become overwhelmed. Additionally, to get a lot of this information, we actually had to open the email to start. In order to see the contents of the email, we had to interact with it in some way. This is inherently risky as soon as we open the email, we are exposing ourselves to auto-downloaders, as well as potentially accidentally clicking a link or downloading a file. So the less we can interact with the email from our system directly, the better. This is where we can see a transition into our AI model. So now let's look at how the AI model would interpret this email or process this email. So first, there would need to be some sort of automatic data ingestion pipeline that feeds incoming emails to the AI model. Creating this pipeline is out of scope for this demonstration, so let's assume that this data ingestion pipeline has been created and this email is automatically being parsed and sent into our AI model with the necessary details extracted. And our AI model ingests CSV files as they come in from this pipeline. We'll be using the same AI model we created in the previous demonstration of this course, which as a reminder, works by looking at the contents of the email, performing a word count and frequency analysis on that contents, and comparing it against its known statistical spam emails to see whether or not an email is spam. So let's get started. On the screen, I am in a Python interactive terminal, and this is the same interactive session that we were working in, and this is the same interactive session from the previous demonstration. So the first thing we need to do is read in the CSV file that contains our extracted features from the potential spam email. So we'll call this data feature set and set it equal to pd.read_CSV. And then we'll read in the extracted features from the pipeline, which in this case has been put into unknown email data.csv. Next, we'll make a variable called email contents and set that equal to feature set at v2. And if we examine the variable email contents, we can see that it contains the text of the email. Now we need to transform email contents into the word frequency analysis format using our word counter count vectorizer. And so we'll call this email contents formatted and set it equal to word counter.transform and pass it email contents. And now if we look at the output of email contents formatted, we can see that it is a NumPy array, and if we print the contents of it, we can see that it has the same frequency output that we saw in the previous demonstration. So now we have the contents of the email put into the proper format to feed into our AI model. So at this point, we can call spam predictor, which was the name of the model that we created, .predict, and we can pass it this email contents formatted. And in the output, the AI model has told us that this email is spam. All of these steps that we've taken could be put into an automated pipeline so that we don't need to perform any manual steps from data ingestion to having the AI model output a result. And there are a lot of advantages to this. Right away, we can see that the AI model is much faster at processing whether or not an email is spam. So if we're doing this at scale, we aren't going to run into that overloading issue. Also, we can do all of this in an isolated sandbox and avoid ever interacting with the email or its contents in a dangerous way. This protects all of our critical systems from any potentially dangerous emails. So this has been a comparison of traditional email security techniques with an AI-enhanced security technique method. In this video, we're going to demonstrate how an AI model could detect abnormal changes in user data through anomaly detection. In this case, we're going to be taking a look at inflation values over the years and doing anomaly detection on those inflation values to find out which years represent anomalies. In this way, we are detecting abnormal changes in our data based on deviations from the norm. The first thing we need to do is obtain our dataset. To do that, we're going to download the inflation and consumer prices dataset from the World Bank. So if we navigate to the URL seen at the top of my screen, which is https://data.worldbank.org/indicator/fp.cpi.totl.zg, and then under the download header on the right-hand side of the screen, we click on CSV. This will download a zip file of our dataset. If we open up the dataset CSV file in the zip file that we just downloaded, we see that the information looks like this. The first thing to note is that the first 4 lines of this dataset are extraneous data that we don't need, so we can delete these first 4 lines. Now our dataset should look as follows, with the first row representing the headers of all of our different features, and the remaining rows representing our data. Now the first thing to note is that this dataset gives us the inflation value by year for each individual country. So what we're going to have to do is perform some sort of aggregation on this data to get a single data point representing the inflation value for the world in that year. If we return to the original World Bank data page, we can click on this Details button above the chart, and it tells us that the aggregation method they used is median, and that median value generated this world inflation value chart. So in our case, we're also going to be aggregating our values based on the median of the inflation values for every country in that year. So once you have made the change to your dataset by removing the first 4 lines, save your dataset and call it something like dataset_formatted.csv. Now let's get started with creating our model. The first thing I'm going to do is show the contents of the directory that I'm going to be working in by using the command dir. And we can note that our dataset formatted.csv, which is what I've called our dataset, is located in the same directory that I'm going to be working in. Next, let's go ahead and install some of the libraries for Python that we're going to need for this demo. I'll use the command pip3 install, and then we're going to install NumPy, Pandas, PyArrow, and scikit-learn. In my case, all of these libraries are already installed in my virtual environment, but in the case that you didn't have them installed, this command would install the libraries for you. Next, let's start a Python interactive session using the command python. The first thing we're going to do now is import some of these libraries. So we'll import NumPy as NP, then we'll import Pandas as PD. Next, we're going to import the specific algorithm in the sklearn library that we're going to be using for our machine learning model, and we'll go into more detail about that as we actually use it. But for now, we'll use the command from sklearn.neighbors import local outlier factor. Now that we have our libraries imported, let's go ahead and load our dataset into memory. We'll make a variable called dataset and set it equal to pd.read_csv and pass it the name of our dataset, in this case, dataset_formatted.csv. We can examine our dataset and see what it contains using the command dataset.head. And we can see it looks very similar to what we saw when we opened it in Excel. we have a column with country name, the country code, an indicator name, indicator code, and then every other remaining column is a year, representing the inflationary value for that country in that year. Now, let's go back to what we talked about earlier, where we need to aggregate this country data into one single world value using the median of the dataset. We'll do that by creating a variable called world median by year and set it equal to dataset.select_dtypes. We'll pass it include equals np.number, which will handle the cases where we don't have a value for inflation for a given year in a given country, and then call .median. Now we can inspect world median by year, and we can see in the output in the first column we have the year value, and in the second column we have the associated median inflationary value for the world in that year. Now we have our data in the format of a series. Let's reformat it back into a data frame. So we'll make a new variable called world median by year dframe and set it equal to pd.dataframe and pass it world median by year. Now let's assign some names to our columns of the new data frame by first resetting the index by calling world median by year dframe.resetIndex and setting inPlace equal to true. And now assigning the column names of year and inflation to the first and second column respectively by calling world median by year dframe.columns and setting it equal to year and inflation. Now we can inspect world median by year dframe to see what it contains. And now we can see that our series has been transformed into a data frame with the columns year and inflation at the top. Now we are ready to start training our model. And this is where the library from sklearn that we imported earlier, local outlier factor, is going to come into play. This is the algorithm that we're going to use to train our AI model to look for anomalous or abnormal data. The local outlier factor uses a density-based approach to determine whether or not data is anomalous. By looking at its neighbors and using a distance function to calculate and compare against its neighbors, it will determine whether or not a given data point is anomalous or abnormal. So first, we're going to instantiate a local outlier factor by creating a variable called LOF and setting it equal to local outlier factor. Now let's use that model to both fit and predict on the inflation values in our world median by year dframe value. So we'll make a new variable called LOF_predictions and set it equal to LOF.fit_predict, and we'll pass it world median by year dframe and then pass it the inflation values. Now let's create a new column in our world median by year dframe and insert those predictions into that column. We'll do this by setting world median by year dframe at anomaly equal to LOF_predictions. Now we can once again examine our world median by year dframe. And we can see that now we have three columns, with the third column being the one that we just added, telling us whether or not an inflation value at a given year represents an anomaly or an abnormal value. So let's go ahead and print out the entire data frame and see which years the model has determined as being anomalous or abnormal. And so in the terminal, I've now printed out the entire data frame, and we can see that anywhere in the anomaly column we have a value of -1, the model has determined that that particular data point or that year is an anomalous or abnormal value. So the years that have been identified as anomalous are 1974, 1980, and 2015. However, we can't necessarily take these results at face value because we didn't tune the parameters of our model at all. We took the default number of neighbors that the local outlier factor model compares against, which is 20, and used that. However, it's critically important that we tune this number of neighbors value to our data set in order to get accurate results. Now, the proper tuning of this takes a lot of time, and it's important to get this value right, but for this demonstration, let's just try using a different value, such as 10, and see how it changes the results. So I'm going to recreate the model, once again by calling LOF equals local outlier factor, but this time I'm going to pass an argument, n_neighbors equal to 10. And then we can run through the same steps again and create the predictions and print out the entire data frame. So in this case, with a new number of neighbors value, the model has detected that 1974, 1975, 1980, 1981, and 2015 are all anomalous values. So we can see how important it is to tune our model correctly because it can greatly influence the output of our model and the accuracy of our results. So this is one way that we can use to detect abnormal changes in user data or do anomaly detection with machine learning. In this demonstration, we're going to look at a comparison of AI-powered anomaly detection, or an AI model that can detect abnormal changes in data, against more traditional methods of detecting those anomalies or outliers in our data to see how much this AI model helps us in terms of doing anomaly detection. So for our baseline comparison, the AI model we're going to be using is the model that we created in video 8. As a quick recap, on the screen in the terminal, I have the steps that we used to create the AI model, and then as a reminder of how this model works, this model tries to detect abnormalities in a dataset containing inflation values for the world during a given year. It does this using a local outlier factor algorithm and comparing each data point against its corresponding neighbor. And when we use this AI model, we get an output similar to what you see on the terminal here. We have a column for the year, a column for the inflation value at that year, and then a column labeled anomaly telling us whether or not that year represents an anomalous or abnormal data point. If the value is a -1, then that means that particular data point or that particular year is an abnormal year. So when we use a default value of 20 as the number of neighbors to compare to, we get the years of 1974, 1980, and 2015 as being anomalous years. Let's take a look at a more traditional way that we could try and perform this anomaly detection to see if we can come up with the same results and what level of effort is going to be required to come up with those results. There are a huge number of different statistical methods, tools, and techniques to perform manual anomaly detection on datasets. In this demonstration, we're going to be using a common one, which is to look at your dataset in Excel or some other spreadsheet tool and try to identify outliers or abnormalities using the tools in Excel. So on the screen, I've opened up our dataset in Excel. Now the first problem that we have is that the dataset itself does not show us the inflation values for the world, but rather for each individual country at a given year. In our previous demonstration, when we built the AI model, we used a median aggregator method to get a median value of inflation at a given year for the entire world. So at the bottom of the dataset, I'm going to add a new entry called world. And this is where we're going to have the median value for all of our columns. So now I need to calculate that median value. I'm going to use the Excel function median, and I'm going to pass it the range E1 to E266. And that gives us the median inflation value for the world in 1960. And then I'm going to apply this same median function to the rest of the years. For easier clarity of what we're doing, I'm also going to freeze the first column and the first row of our dataset so we can always see the titles. Now we have our column and row frozen, we can start to try and perform some manual or traditional anomaly detection. The first thing we can do, and the simplest method, is to just scroll through our data and look at it and see what sticks out to us as being different. So as I scroll through the world row, I see a value in 1974 that sticks out to me as being 17%, 1975 as being 13%, 1980 and 1981, which gives me 13% and 12%. Now let's highlight the columns that our AI model detected as being anomalous to compare how our ad hoc visual method compared to the AI model's results. So the highlighted columns are the ones that were detected as being anomalous or abnormal. So we can see that the one that stuck out to us, 1974, was indeed also detected by the AI model. Similarly, 1980, which we also identified as being anomalous visually, was also identified by the AI model. However, 1975, which we characterized visually as being anomalous, was not detected by the AI model as being anomalous, even though its inflation value is fairly similar to 1980. Scrolling forward, our AI model also detected 2015 as being an anomalous value, even though we didn't detect it when we did a visual inspection. So we can see that the visual inspection is fairly ad hoc and unreliable. Sometimes we get it right, sometimes we don't, and we're subject to our own internal or personal biases. For example, when I did the visual inspection, I fell victim to a bias of looking for high inflation values, but not recognizing that low inflation values can also be anomalous or abnormal. So right away, we see that the AI model has an advantage over the ad hoc method in that it is repeatable and more reliable. So let's try to refine this ad hoc method and see what else we can do. Let's translate this row into more of a column format to try and see if we can do something on it in a different format. So now on this sheet in Excel, I've extracted our world inflation values and put them into a column, with the first column being the year associated with that value. So now let's try a method that is similar in nature to visually identifying the data, but with a little bit more added onto it. Now we're going to sort the inflation values from smallest to largest to see how that impacts our anomaly detection. So now, from top to bottom, our data has been sorted from smallest to largest in terms of inflation value. And here we can see that 2015 is very clearly an anomaly because it is the lowest inflationary value in our data set. And 1974 and 1980 are both the highest values in our data set. So that makes sense as well. So by sorting the data and looking at the smallest and largest values, we can identify visually the abnormal values that the AI model identified as well. However, this still takes a significant amount of work in terms of translating and analyzing the data, and we're still not doing this very scientifically or in a robust, repeatable way, because we don't know why the AI model detected the bottom two or two highest values, but only the single lowest value. So we're getting closer to mimicking the AI model's behavior, but without really knowing why we're doing it. So we're still a little bit in the dark here. So let's try a more statistical approach and see what we can do. One statistical approach that we can do is using quartiles. The first quartile of our data is going to be a value which 25% of our other values are less than, and the third quartile is going to represent the value in which 75% of our values are less than. So let's try calculating that and seeing what that tells us about outliers or abnormalities in our data. So to do that, I can use the quartile.inc function in Excel and pass it the range of all of my inflationary values, and then give it the argument 1 for the first quartile and the argument 3 for the third quartile. And this tells us that our first quartile value, of which 25% of our values are less than, is 3.25. And our third quartile value, of which 25% of our values are greater than, is 9.02. So now let's add a column called anomaly, in which we will use these values to identify whether or not a given row is anomalous. To do that, we will next need to get the interquartile range, which represents half of our data between the first and the third quartile. This is going to be the subtraction of the first quartile value from the third quartile value. Now we can use this value to calculate the lower limit and upper limits beyond which anything would be considered anomalous. Let's calculate our lower limit first. The formula for our lower limit is going to be the first quartile minus 1.5 times our interquartile range. And the formula for our upper limit is going to be the third quartile plus 1.5 times our interquartile range. Now, we can set up a Boolean formula in our anomaly column to tell us whether or not a value is anomalous based on whether or not it is less than the lower limit or greater than the upper limit. And when we do this, we find that none of our values are anomalous, at least not by this method. None of our values are less than negative 5.4, and none of our values are greater than 17.68. So using the statistical method, we have a more repeatable, science-backed method of detecting anomalies, but in this case, we haven't detected any anomalies. So at this point, we would have to start going deeper and using other statistical methods or finding different tools to start trying to find anomalies. But we can quickly see the comparison already. Using the AI model was much faster and much less work-intensive to do anomaly detection than trying to perform these manual statistical models. That's not to say that these manual statistical models don't have their place, and they can also be automated. However, having the AI model in the tool belt provides us with significant value in terms of how quickly we can perform this anomaly detection, as well as how scalable we can make it. In this video, we're going to look at how we can ensure and validate the integrity of our AI model. For the purposes of this demonstration, we're going to be working with the same AI model that we created in video 8 using the linear outlier factor algorithm. And as a reminder, that model was called LOF. So the first thing that we need to do is export our model. To do that, we're going to use a library called joblib. So we're going to use the command import joblib. Next, we'll export our model using the command joblib.dump, pass it the name of our model, which is LOF. Then we'll pass it a string representing the name that we want to export it as. And in this case, we'll call it lof_model.pkl, and then pass it a compression level, in this case 9. Now at this point, we have exported our AI model as a .pkl file into our working directory. Now, as the first step to verifying or ensuring the integrity of our AI model, we next need to export the checksum of our model. So to do this, we're going to use a library called hashlib, and we'll use the command import hashlib. And now we'll use hashlib and the associated SHA-256 algorithm to create a checksum of our file. So first, let's instantiate an instance of the SHA-256 hasher, and we'll call it m. So we'll set m equal to hashlib.sha256. Now we will call m.update, and we're going to pass it our model. So we're going to pass open lof_model.pkl, and we're going to open it in read bytes mode, .read, and now that we've updated our hasher, we can call m.digest to get an output of our checksum. Now, m.digest gives us our byte string, but more likely we want to get this output in hex characters, so we could also call m.hexdigest. And we have the output, which represents the checksum of our AI model. So now at this point, what we would do is anywhere that we are using or distributing our AI model, we would distribute this checksum or hex string along with our model so that prior to any time we or anybody else uses the AI model, they could run their own checksum calculation on the file that they have been given and verify that the output matches the hex digest that we have generated here. In this way, we can verify that our AI model, as we have trained it, has not been tampered with or modified in any way, because as soon as there has been any modification made to our AI model and the associated exported file, this checksum value will change. And if there is a mismatch, then we know that we should not be using that AI model, and somewhere along the way, whether incidentally or on purpose, the AI model has been tampered with and modified. So this is one way that we can use to ensure the integrity of our AI models. To see this in action, let's write a quick function that will compare checksums and tell us whether or not they are the same. We'll start by storing the hex string that we just created in a variable called checksum. So we'll say checksum equals m.hexdigest. So this represents the checksum that we would package along with the AI model. We would be given this along with the AI model, or we would give it along with the AI model. Next, let's create a function called checker. And as an argument to this function, we'll pass a file name called f. And inside this function, we'll create a SHA-256 instance called checker by setting checker equal to hashlib.sha256. Then we'll call checker.update, and then we'll pass it open, and we'll open the file f that was passed to the function. We'll open it as read bytes. We'll call .read on that. And then we will return whether or not checker.hexdigest is equal to checksum. And now we can try this out on a few different files. So first, let's try our AI model. And we can see that the output is true, telling us that we have the correct file and the file has not been tampered with. If we call checker on a different file, such as our dataset, which is dataset_formatted.csv, it tells us that this is false. So in this case, if somebody tried to pass us dataset_formatted.csv and told us it was the AI model, we would be able to tell that it is not the correct AI model because the checksum doesn't match. So this is a practical implementation of verifying the integrity of an AI model.
So I really want to show you what you could expect if you had an AI-based network detection response system on your network. So this is a Vectra.ai deployment that I have set up. I have 3 sensors set up along with a brain. So each of my sensors is sitting at a remote branch office. And what you do is you set up a span port on your switch and you send all network traffic to the Vectra brain and to the sensors. It then collects metadata on this and sends it back to this brain for processing. Once it's done processing, it will determine if something's anomalous. And the way this works is it actually builds behavioral patterns based upon every IP address on your network. What's normal activity for this IP address? What's abnormal activity for this IP address? And what I've done is I've created a couple of scenarios here that you could see with a system like this. So the first one is a detection that I've set up here for an SMB brute force. Now, I use this against an actual desktop machine within the network just to show you what this looks like. So when I did this, it immediately alerted of the intrusion detection attempt because it saw a large number of attempts to log in to this SMB account. And we can see here that the internal target was 10.0.1.23. And we can see there was 208 attempts, which returned an access denied, prior to finally seeing an attempts where error code was returned of success, meaning that it's highly likely that at a certain point the individual is able to gain access to that specific device. So what I would do in this case is I would download the PCAP and I would open that in Wireshark and I would go through and determine where the source of the information came from. In this case, it came from 10.0.0.1. What was the activity it was doing? And I can go and I can take a look and do a root cause analysis. And what this does is it significantly reduces the amount of time I need to spend looking through log files on various servers or looking through SIAM events on various servers because this will actually alert me. And in fact, this is actually integrated with our SIAM solution. So when Vectra does create an alert, it will automatically pop up for us and we can go and investigate. But this is one where I actually legitimately did the attack, gained access, and we can see that here it alerted. And this is what you should expect if you're implementing an AI-based detection system on your network. However, this is another detection, and this one is going to look incredibly odd. So this is a machine I set up, brand new machine, never before seen on the network. And here we can see that, hey, wait, this was accessing Outlook.office365.com on port 443, and sending data. Well, this is an actual false positive. Because the system does not have enough information on this specific device when it's set up, what you will see is that it's going to generate some false positives initially because it has not established a baseline yet for what is typical traffic of this machine. So this is a false positive. I know it's a false positive because I went on this device, I went to outlook.com, and it threw this alert. And I see this all the time with new machines when we put them on the network. We see the AI alerting false positives for the first couple of weeks. The first time someone downloads a bunch of files from their Office 365 account or OneDrive, we'll get alerts. The first time someone logs into Outlook, we'll get alerts. The first time someone accesses an SMB account, we'll get alerts. And that's pretty normal of new machine setup, and we know what to look for after a while. However, this can be problematic if your organization is incredibly large and you're deploying lots of machines all the time. So you have to keep in mind that when you're using these AI-based systems, there is a learning period involved where they don't know what is normal behavior. They haven't really built a model of normal traffic and normal behavior for that host yet. So suddenly, when it starts seeing information and traffic on it, it's going to throw an alert. And in this case, it did. We investigated it. We will close that off. I don't have to download the PCAP for this. I know what it is. So I'm on VirusTotal. Now, VirusTotal is a service that you can use if you have a file or a piece of code and you need to do some analysis on it to determine if it's malware or not. You can upload it here, and it'll be able to return you some information on it. Now, recently, they have released this, what is called crowdsourced AI. Now, what this does is this uses a large language model, and it'll take the file and it'll strip out any system commands it's running, and it'll strip out any macros that it's running, and it will actually analyze the raw text of the macros, and it will return to you what that is actually doing and whether or not it's benign or whether or not it believes that it is malicious. So here's an Excel spreadsheet, just your standard Excel spreadsheet, what you'd typically find in most organizations. And we can see here that this one's being flagged as benign. If we go down, absolutely no antivirus systems are detecting this as being malicious, but it actually explains to you what the system's doing. So it says in sheet 1, there's worksheet change event that triggers when a change is made to the worksheet. And it does it in this column. Now, that's fantastic because this is able to give you some insight into what the actual script is doing, and it allows you to go a little bit further on your investigation outside of just isolating the system and removing it. Now you can actually see what the infected system was doing, what it was targeting, what commands it was running, and you may be able to actually harden your environment using that information. So here's one that was actually detected as being malicious. So this is another Excel spreadsheet because Excel macros still infect a lot of organizations every day. And here we can see there's 3 variables that were in this file, apple, banana, and cherry, and they all contained base64 encoded strings that, when decoded, were executing a PowerShell script called revshell.ps1. So what this was doing was this was creating a reverse shell when you would run this. And we can see that a lot of antivirus systems were detecting this as what it is, which is a reverse shell. However, we can also see that there's some down here at the bottom that were not detecting it as a reverse shell, and some of these are pretty big names. So Sophos, McAfee, these are household names, Malwarebytes. These are not small antivirus systems. These are ones that often will have an actual corporate representative or corporate representation. So this is indicative of some of the issues you may see where this could actually run on a system if you're running one of those antiviruses and you'd never know. However, you're able to take that file and put it through here, and you're able to get that AI to do an analysis for you to tell you what it is doing. What is that exact Excel spreadsheet doing? So here's a .doc. Same thing. We have a macro, it's malicious, and it's within this .doc file. So The large language model takes that raw text, analyzes it, and it tells you what it's doing. So it tells you that there's a PowerShell command that's obfuscated using base64 encoded, and it gives you the base64 string. And then when you translate that, it tells you new object system net web client, download string, and then it's downloading run.txt. And then it's going to actually execute that using an invoke expression or an IEX commandlet. So this is typical download dropper behavior, and we can see that it is being picked up by a lot of antiviruses, but at the same time, there's some other ones here that are not picking that up. Trend Micro, Sophos, Fortinet, they're not actually detecting this as being malicious. However, when we run it through VirusTotal, the AI is showing to be a tremendous utility in determining that it is malicious. So as these antiviruses go out and implement large language models within their systems, they're going to be able to run an output and give you not only, malicious file detected, but it'll actually be able to tell you specifically what that malicious file was doing and why it's malicious. And here's another one, and this isn't actually a file, but this is code that was being run. So this is actual code that's dropped in to be analyzed. And it tells you that this is a Discord bot attempting to steal Discord tokens from users. And it'll tell you exactly how it's working. And we can see here that, once again, when this is run, not all antivirus systems pick this up. So we can see that the power of LLMs even today, as these are still relatively in their infancy as far as usability within corporate environments are concerned, are able to provide tremendous insights for us as cybersecurity professionals and analyze files and tell us if there's anything malicious internally or not.